Okay, and now we're going to add a little bit of a variation into this thought about the curl. So when we looked at the Khan Academy videos, we were pinning down a sphere into this vector field, and the sphere ended up rotating around a particular axis that was going to give us its maximum rotation, and that axis was in the direction of the curl. Here's the variation we're going to do now. We're going to determine the axis around which we're going to force the sphere to rotate. So we're now going to call the axis, I'm going to call it n hat, and I'm purposely using n hat because yes, in a moment we'll see this is going to be a normal vector to a whole surface. So you can imagine you have a surface and we are putting a paddle wheel now normal to the surface. And if that normal vector n is not pointing in the exact same direction as the curl, then we're going to get a different rotation speed than we would have if we had just let the paddle wheel rotate around the axis that it most naturally would rotate, which is the curl axis, right? So if I'm no longer just pinning down the center of the sphere and allowing it to rotate around some given axis, but instead I'm saying you must rotate around this one and then see how it gets pushed given to the vector or given the vector field, then we're going to get a different rotation speed. And so we're going to quantify that actually by using a projection. Notice what happens when I take the dot product between the curl vector and then this new n direction, which you can picture as like the way I'm pointing my handle now. And physically, let's look at it physically first. It's going to be related to the projection. That's what's showing up there. Physically, if I project this curl vector onto my normal vector n, I'm going to get this new projection vector. And the scalar component of that projection vector will be given directly by the curl dotted with n. And let's remind ourselves why. When you take the dot product between a vector and a unit vector, you're left with just the scalar component of that original vector in the direction of the unit vector, because this will just be 1. And so you can just see again from geometry that this scalar component is just going to be the magnitude of the curl and then times the cosine of the angle between them. Okay, so what we're going to get is now a number when we take this dot product. It could be positive or negative. So we're going to call it assigned, because it can be positive or negative. It's going to be the signed rotation speed of the paddle wheel if you are assuming or requiring it to rotate around this new direction n. And so similarly to what happened with curl, if this has a positive value, then it's telling you the paddle wheel is rotating counterclockwise. And if this scalar component has a negative direction, then it's telling you the paddle wheel is rotating clockwise. And so here's 2 examples where we have this vector field here, F. And as you can see, we're choosing the direction that we're placing the paddle wheel into this flow. And then we're going to see, does it rotate or not, and at what speed? So we can see right here that I'm not going to get any rotation from this N2 direction because I've aligned the paddle wheel in the direction of the flow. And that means that if I take my curl vector, which is really your direction of maximum rotation that you would get in this type of flow, if I take that vector and then I take the scalar component or dot product with this normal vector, I'm going to get 0. So there's no rotation happening when I put the paddle wheel this way. As opposed to here, with N1, I would expect that when I dot my curl vector with the normal vector N1, I'm getting rotation. And because it's going counterclockwise, I would expect this quantity to be positive. Okay, so, and you may be saying, wait, why are we doing this? And I get it, like there's no reason right now why we should be picking the direction of the paddle wheel. We're about to show you where that's coming from. But I think it's a little bit easier just to say, hey, take the curl and here's what happened when you dot it with the normal vector, and here's what it means physically. I like starting with that visualization before we get into the main theorem where this comes up. Okay, and then in 2D, what's great is you have two options for n hat in 2D. N hat can either be positive k hat or negative k hat. And so if we let n be positive k hat, then this is again going to give us the signed rotation speed of the paddle wheel at a given point. And so this is now, I want to be really careful that you understand what this is not what you're thinking from physics. We're literally, what I was trying to draw here is like you're looking down on a paddle wheel, like one of the ones, something like this. That's literally what I'm trying to draw with those little X's. So it's not our physics notation. It's just imagine you're looking down and you are placing that paddle wheel and seeing which way it's going to spin. And then same thing here, we're just putting it in the flow. In both of these cases, my paddle wheel handle is pointing out at us in the positive K direction. So that's why it's a little bit confusing with the physics notation. So this was just to help us visualize a paddle wheel, and we have the handle coming out at us. All right, so in this case, part A, the sign of this, I don't have any rotation happening when I place the paddle wheel pointing out at us into this flow, because it's actually a uniform flow at all points, and so I'm not going to get any spin. But here in part B, you can see because it's spinning faster, or excuse me, the fluid is flowing faster down here than up here, we would expect we could get some counterclockwise rotation if we put the paddle wheel in where the handle is pointing in the positive K direction. Okay, and so let's actually now see what this quantity is for a general vector field. And then we're going to come back and interpret it when we see this pop up in our theorem. All right, so let's actually calculate the curl. We remember from the previous calculations on the previous page. If I have a general vector field, and I'd like to find the curl, I'm always doing this determinant of this 3×3. And I can know right away, you can try it out here if you'd like, but I know right away because this is only a two-dimensional vector field, my curl is only going to have a K component. So my only option here is just to jump to the K and see what that's given by. But you could also just do that out and check, verify that you agree. When we get to the K component, I have the partial of Q with respect to X minus the partial of P with respect to Y. Okay, so this is I'm just going to write it as a vector, 0, 0, and then partial of Q with respect to X minus partial of P with respect to Y. That's a general curl vector for a two-dimensional vector field. Now, if we want to find the K component of that, so I take that curl vector, project it onto the K vector, and say, what's the scalar component in that direction? You can notice K is just the vector 0, 0, 1. And so it's literally just going to give me the K component of the curl. You're just going to get this quantity. Okay, so I want us to think of that. We're going to come back to this in a minute. Now we're going to move to our big theorem. And in our big theorem, we're going to see this K component of the curl is going to show up. And it's going to allow us to have a nice interpretation of it. Because when we see it in the theorem, we'll see how it ties to the circulation around the boundary of a curve. So let's try that next.